This is going to take the place of the meeting that we were going to have when we were so rudely interrupted with the internet going south on Thursday. Thank you for your patience while I stammer through the sharing of the whiteboard. Let's do a quick reminder of the sign conventions for the process energies or path energies that we've already discussed in the course. Remember that for heat transfer, if Q is greater than 0, that means that heat energy is absorbed, because that's what's necessary for some stuff to increase in temperature. And likewise, if Q is less than 0, then heat energy is released. And correspondingly, that stuff that we're studying is going to decrease in temperature if it's a bulk stuff in a solution or a gas or what have you. We introduced on Tuesday the concept of work and what happens when we actually take some stuff and compress it, or take some stuff and expand it. And gases are what we're talking about there, because those are stuffs that have volumes that are compressible or expandable very easily. If work is greater than 0, that corresponds to work being done on the system. That corresponds to us coming in from outside and investing work into the system. This corresponds to the piston in the container from Tuesday, where we compressed its volume. Delta V was negative, so work turned out to be positive. If work is less than 0, work is done by the system. That corresponds to our container or our piston increasing in volume and pushing out against some external pressure. Okay, these are common statements. These are common ways of expressing what is actually happening when heat transfer is imposed on a system, when work is imposed on a system. Now, I have to do a bit of apologizing here to the 930 people, and really to everybody, but the 930 people especially. I introduced the first law of thermodynamics when we were finishing up class on Tuesday. And my presentation of the first law of thermodynamics looked something like this. And what I said in response to that was internal energy change, which is represented by delta U, is equal to Q plus W. Now, I'd made a statement to the 8 a.m. class that delta U is a really obnoxious symbol for internal energy, because there is no U in the word internal or in the word energy. We do this a lot, those of us who do physics and physical chemistry. We run out of letters to use in our symbols, and we just pull letters out of seeming thin air. And I use delta U because for internal energy, I've been using delta U for most of my life. But I told the 8 a.m. class I'm going to try to break the habit of using delta U for internal energy, and I'm going to use a symbol set that's more rational. Delta E for energy, because energy starts with E and such. Okay, and just to make absolutely sure that it's internal energy that we're describing, I'm going to subscript the internal with an INT. Okay. And it's actually somewhat fortunate that I've done this because there are some problems in the homework where delta E stands for internal energy and delta U comes up, I think, once for internal energy when you're going through the homework. When you go through the textbook prefers delta U for internal energy, although it does make comment that sometimes delta E is used for internal energy as well. We want to make sure that we use the most consistent symbol set possible. Either way, whichever way the mathematics is presented to you, the meaning is the same. The sum of the two process energies, heat and work, add up to the change in internal energy in the system that heat is transferred into or out of, and that work is performed on or by. The sum of process energies for a system is equal to the change in the energy inside that system. And this is an alternate way to state the first law of thermodynamics, or what you have heard of before as the law of conservation of energy. Energy cannot be created nor destroyed. Energy is simply transformed from one state to another. Let's talk through an example of this type of problem that will turn up. System releases 4,500 joules of heat energy and 2,500 joules of work is done on the system. What's the change in internal energy of the system? You'll see problems turn up like this in the homework, and the cue for the problem is it's an interpretation problem. The phrases that are involved in the problem are the phrases that you need to be able to recognize to actually describe what is happening to the system. For this particular story, and I'll go ahead and use the rational symbol set here, internal energy change is equal to Q plus W. We need to identify Q. Q is heat energy transferred. In this particular story, yet heat energy is released. Our sign convention says that if heat energy is released, the Q for that transfer is less than 0. So a system releases 4,500 joules of heat energy corresponds to a Q that is negative 4,500 joules. 2,500 joules of work is done on the system. If work is done on the system, energy is invested into the system. And our sign conventions tell us that when work is done on the system, that corresponds to a positive value of W. So the heat energy that's released overwhelms the work done on the system, and the internal energy change in the system. See, I just did it again. Very naturally go for delta U. The internal energy change in the system is negative. And that's the answer, and that's all there is to the problem. Problems of this sort are exercises in recognizing the language in the problem and corresponding that language to a specific sign convention for, in the first case, heat transfer, and in the second case, work done. And it's important for you to recognize those sign conventions and recognize the language that's used with those sign conventions. So that's important thing number one for this mini video lecture. Important thing number two is the identity of my energies here. Remember that heat and work are process energies. I don't know why I'm trying to draw E's with 4 crosshatches. Process energies are properties of a transition in a system, properties of a process taking energy from one place to another. And I think I said this to most folk when we were talking on Tuesday, but I'll reemphasize it here. You're never going to see a delta Q or a delta W in any work that we do, pun not intended. Heat doesn't change. Work doesn't change. Heat is transferred. Work is performed. And that major distinction between the process energies and the state energies is something very critical to how we describe energies in thermodynamics. Internal energy is a state energy. State energies can have initial and final values. In fact, the change in state energies is solely defined by the initial and final values that that energy has. And it's a property of the initial and final conditions of the system. I can tell you that a system has an internal energy at one point in time. I can't tell you a system possesses heat, And I can't tell you that a system possesses work. But critically, in how we're going to build our descriptions, it's going to be very useful for us to talk about heat as if it were a state energy, even though heat is not something a system possesses, but something that is transferred from one place to another. Let's bring up an example of this. Where'd my example go? Here's my example. You should recognize this example from Tuesday. Okay. The reaction we were talking about where we had hydrochloric acid and sodium hydroxide combined, and by knowing what happened in the aqueous solutions of hydrochloric acid and sodium hydroxide, we were able to identify some amount of heat released when we combined the two and made salt and water. And this is very characteristic for chemical reactions. When we actually combine two solutions, we receive out, in a lot of the time, some amount of heat energy. Now, this gives us cues about the chemical reaction afoot here. It tells us that there's some property of this chemical reaction that corresponds to release of heat energy. More to the point, there's something that the products possess. Oh, excuse me. There's something that the reactants possess that's getting released as the reactants are transformed into products. And the heat is a cue, is a signature of that thing. I'll come back to this story here in a little bit. I said I'll come back to this story here in a little bit. That's the story I had up here before. Goodness. My whiteboards slide all over the place. Thank you for your patience. Okay. So here we are. What we need to have is some corresponding value of heat that describes what happens in a chemical reaction of that. It's important to mention at this junction that most chemical reactions that we're going to study are processes that happen at constant pressure. It turns out that internal energy change does correspond to Q alone if I can hold volume constant. If volume is constant, no work is done. If no work is done, delta E internal is equal to Q. But we don't deal with reactions happening at constant volume a whole lot. Okay? That would imply that I have some closed container that the reaction is happening in, and not only can no air get in or out of that container, the container can't expand or contract. Okay? Most of you now have done the experiment from the lab where you captured carbon dioxide over water. And we used water so that water could be displaced, so that we had a system that wasn't a constant volume system, but a system where we could change the volume present. And we could watch that change as carbon dioxide bubble through the water. It's much more proper to say that those experiments happen at constant pressure. And as it turned out, I kept very close tabs on the pressure in the region while our experiment was going on. And that pressure stayed right about 1.004 atmospheres. It could have been 1.0036, it could have been 1.0043, but I always rounded back to 1.004. To four significant figures, the pressure in that lab was constant. And that is a fact of most laboratory conditions we work under. They're constant pressure conditions. Enthalpy will be a new state energy for us. Enthalpy is a thing we will define to be heat transfer at constant pressure. Now, your textbook goes through an exercise that demonstrates that enthalpy is actually a state energy, and we treat enthalpy as a state energy in the same way we treat internal energy as a state energy. But that particular exercise is a little bit deep theoretical for what we want to accomplish. And quite frankly, it would be a little bit of a punchline to a joke that a lot of folk wouldn't get. So I'm going to leave that particular proof alone and just let it sit in your textbook. I am simply going to say that the definition of enthalpy, which we can't use delta E for enthalpy because I'm already using delta E for energy. But enthalpy uniquely has an H in it. So I'm going to use delta H for enthalpy. I'm going to say that delta H is defined as heat transfer at constant pressure. And what enthalpy turns out to be is the thing that our reactions possess before and after that expresses itself in the chemical reaction, in the measurements of the evidence of the chemical reaction as heat. There it is. Like I said, hydrochloric acid and sodium hydroxide possess something that when they are combined releases heat as the reaction goes forward. That something that they possess is what we're going to term enthalpy. And enthalpy is traditionally expressed in units of kilojoules per mole. And how that works out for a situation like this, 50 milliliters of a 1.00 molar reactant, like we expressed in the hydrochloric acid problem from Tuesday. Well, Let me just rewrite 50 milliliters, convert that to liters. And let me just do the same conversion for sodium hydroxide over here. 50 milliliters is 0.0500 liters. Okay, and molarity units are moles per liter. So I can totally convert this volume of hydrochloric acid at this molarity to a number of moles. Okay. The number of moles present of reactants is going to be 0.0500 moles. And the heat that I observe released from this reaction divided by the number of moles turns out to be equivalent to the enthalpy of reaction. I abbreviate reaction with RXN. And I punch in negative 2,900 joules over 0.0500 moles. And the enthalpy of reaction of this story turns out to be negative 58,000 joules per mole. And 58,000, that's very easily converted into kilojoules. And more conventionally, like I said, I'm going to write these enthalpies of reaction as kilojoules per mole. Per mole of what? Well, in this case, because the reaction is 1-to-1, it could be per mole of hydrochloric acid or per mole of sodium hydroxide. Those are the moles present here because there's 1 mole in the reaction of each of these. The enthalpy of reaction for the combination of hydrochloric acid and sodium hydroxide to make salt and water is negative 58 kilojoules per mole of reactant. That's a lot of energy. And of course, there's a lot of acid and base present should I be in a position to react 1 mole of hydrochloric acid and 1 mole of sodium hydroxide. A lot of what we're going to do in the next phase of the course is talk through in detail reactions of this sort and identify ways we can know how much heat these reactions would release if these reactions were allowed to move forward. Put another way, we're going to recognize how much enthalpy is contained in the reactants and the products and reactions of this sort. But in order to go through a story like this, what we need to do is recognize some behavior not recognize some behavior. Let me use proper words. Recognize the way that we see elements appear in nature as a normal condition. So this is one of those moments in our storytelling that I call a word from our sponsor. Let's talk about the elements in their standard states. And I just started listing when I did this in the 8 o'clock section, some examples of elements in nature and what their standard states turn out to be like. And for the most part, standard states of elements are very straightforward to identify. Solids in the periodic table tend to be elemental. And that's true whether those solids are metals, and a metal could be anything from gold and silver to iron to magnesium, even to the alkali metals like sodium. Or whether those are non-metals, like carbon, like silicon, like phosphorus, even beneath oxygen, an element like selenium has elemental behavior. Now, phosphorus does sometimes turn up a little bit wonky, and I'll say something about that in a moment. Remember, there are only 2 liquids in the periodic table as elements. Okay? One of those liquids is a metal, mercury. And mercury we get the symbol of mercury right. There we go. Mercury is a liquid at room temperature, and mercury is elemental. I'll tell you about the other liquid here in a moment. Noble gases are also elemental. Helium, neon, argon, krypton are the examples of noble gases you might come across later on. But noble gases are boring when we actually talk about energetics of chemical reactions, because noble gases don't react with anything at all. It's the other gases that are very interesting. And we remember from coming across these things in chemical reactions before that gases like hydrogen, like nitrogen, and oxygen tend to be diatomic. Don't tend to be, they are diatomic on a regular basis in their standard states. We don't say H, we say H2. We don't say N, we say N2. We don't say O, we say O2. We don't say F, we say F2, fluorine. We don't say Cl, chlorine, we say Cl2. And it's important to recognize that hydrogen, nitrogen, oxygen, fluorine, and chlorine are always diatomic in their standard states. Fluorine and chlorine are interesting because they are gases that are immediately below one another on the periodic table. They're in a column. And it turns out that the other members of that column are diatomic as well. The halogens are always diatomic. I mentioned mercury was the one liquid in the periodic table. The other liquid in the periodic table is bromine, Br2. Bromine is a liquid. The one exception among the non-metal solids that is diatomic is the other halogen, iodine, I2. Strictly speaking, there's another one underneath iodine, which is astatine. But we're not going to come across astatine in Gen Chem 2 ever. Those of you who go on and do inorganic chemistry, you might come across astatine then. It turns out to be very important to recognize the elements that turn up in diatomic form and their distinction from the other elements in the periodic table who are in their standard state are in elemental form. And this comes out when I actually put together a compound like calcium carbonate. Now, there are many ways to put together calcium carbonate. Calcium carbonate is a geologic compound. When I think I misidentified the ore that calcium carbonate comes from when I was in class, I didn't say calcite, which just goes to show just how inarticulate I am when we get to talking about the geologic compounds. And I don't like to put together these things geologically anyway. I just like to put these things together, making them up from their elements and their standard states. If I'm going to come up with a means to assemble calcium carbonate as a solid, I'm going to put calcium carbonate together from 3 elements in their standard states. One is a metal that's elemental, calcium. One is a non-metal that's elemental, carbon. And if I'm going to be complete, I need to make note that carbon shows up as a graphite to put it in contrast to carbon that shows up as diamond. And then a non-metal gas in a diatomic state, oxygen. Now, if we wanted to do an exercise, and you could do this exercise really quick if you wanted to pause the video, I could say, balance this chemical equation. What do you need to recognize about this chemical equation in order to balance it? In order to get all the terms in the chemical equation, one after another, in place. This is where you should pause the video if you're going to do this yourself. If you didn't pause the video, do it yourself, I'm going to do it for you. Or if you did pause it, I'm going to check your work. The most common way to balance this equation is to recognize that I've got an odd number of oxygens over here and an even number of oxygens over here. And what's going to make this thing go forward is to even up the number of oxygens here with a corresponding number of oxygens here. And that just doubles the number of calciums and carbons that we have here. And so I can do that. If you do that, you're not wrong. But if you did that, you didn't balance it the way that I prefer it to be balanced. I was mean to the 8 a.m. class and turned around once they balanced it that way, and I put the arrow there right and followed it right up with CaCO3. And I said, no, you don't get to put a coefficient in front of CaCO3. What do you have to do to balance it now? And after some grumbling and complaining, there was a recognition that the only way to get the equation balanced in that case, no coefficient necessary in front of the calcium, no coefficient necessary in front of the carbon, but the coefficient in front of O2 would then have to be a fraction. And there was grumping and complaining over this because fractions are unsettling, fractions are uncomfortable. The primary complaint that comes up is, how in the world do you ever have 3/2 of an oxygen? It's like you're saying that one atom of calcium combines with one atom of carbon and 1.5 molecules of O2 to make the formula unit of calcium carbonate. And you go, I can't have half a molecule of oxygen. That's pointless. Why didn't I just leave the oxygen as up? And what I ask people to do when they come across that story is not interpret the equation as atoms and molecules. One of the things I try to emphasize when I teach Gen Chem 1 is that there's a molar interpretation of this chemical reaction that is every bit as important as the molecular interpretation. 1 mole of calcium atoms combines with 1 mole of carbon atoms and 1.5 moles of oxygen molecules to form 1 mole of calcium carbonate. I can talk about 1.5 moles much more easily than I can talk about 1.5 molecules. When we write a reaction in this form, like so, that reaction is called a formation reaction. Formation reactions are important to us when we actually study the enthalpy changes in chemical reactions. They're important to us because people who do thermodynamics study these things on the regular and tabulate how the energetics of reactions of this sort go forward. And I actually have a table that is going to be linked off of Canvas of these types of reactions. That tabulation is called a standard thermodynamic properties table. And this is a standard thermodynamic properties table that I personally have put together for our use in this course. It compiles stuff from our textbook and from Sapling Learning's thermodynamic data into one big tabulation. Let me find calcium carbonate on this table. It's a long table. We got 23 pages to this thing. It's got all kinds of chemical substances on it. Here's calcium carbonate right here. Okay? And it has a number next to it that is negative 1207.6. And that column corresponds to this symbol right here, which is a change in enthalpy. It's a change in enthalpy with a degree sign and a subscript F on it. And that means something. Let me take this number into our notes. Is it 1207.6 kilojoules per mole? Let me check that again and point out something in the tabulation that if you've never seen it before might look a little bit weird. Negative 1207.6, I got it right. Now look at the header of this column here, okay? The header reads kilojoules times moles to the -1. Sometimes writing per mole is a little bit awkward, and it's important for us to recognize that we can actually write these without the fraction sign. And we use the fraction sign in other ways in writing out tabulations of this sort. Okay, so kilojoules times moles to the -1 is kilojoules over moles, is kilojoules per mole. Those say the same thing. So I read this value right here as negative 1207.6 kilojoules per mole. Now, what does that represent again? It represents an enthalpy for this reaction. And that enthalpy for this reaction is what is known as a standard enthalpy. A standard enthalpy of formation. Standard enthalpies of formation are enthalpies representing the difference between the reactants and the products of a formation reaction. A reaction where the reactants are elements in their standard state, and the product is some compound whose value is tabulated. If we could react pure calcium, 1 mole of that, with pure carbon, 1 mole of that, with 1.5 moles of pure oxygen, the formation of calcium carbonate would release 1,207.6 kilojoules of energy for every mole of calcium carbonate we made. And per mole is why we want to have this equation balanced, so we have a coefficient of calcium carbonate that's the implied 1. Okay, if we had the balance of the 2 calcium carbonates up here, we wouldn't be able to describe this in terms of kilojoules per mole. We'd have 2 moles here, and we'd have to double this number to talk about the heat energy that's released. Okay. Now, what does standard mean? Standard corresponds to this quantity or this property set that I've talked about previously, which is standard ambient temperature and pressure. Standard ambient temperature and pressure are the normal temperature and pressure that we encounter at room temperature conditions when we're doing work in a laboratory. Ambient temperature, 25 degrees Celsius or 298 Kelvin. Standard pressure, 1 atmosphere. That stands in contrast to STP, which is 273 Kelvin at 1 atmosphere. We don't use 0 degrees Celsius for standard ambient conditions because we don't do laboratory chemistry outside on winter days. We do laboratory chemistry in a lab at room temperature. And I'll use SATP much more often than I'll use STP personally, even though STP turns up an awful lot in the homework. The degree sign on delta H represents standard. The subscript F represents formation. I can talk about one other example of a formation reaction. If you remember us talking about elements in their standard states in Gen Chem 1, you might remember this particular chemical reaction. The formation of glucose. And you obviously would remember that we need 6 carbons up front here. We have 12 hydrogens coming from molecular hydrogen, so we need 6 molecular hydrogens up here. And we have 6 oxygens coming from molecular oxygen. We need 3 molecular oxygens up here. 6 moles of carbon atoms plus 6 moles of hydrogen molecules plus 3 moles of oxygen molecules come up with yield 1 mole of glucose molecule. And I can go back to my tabulation of standard thermodynamic properties. And I can go through, I've got carbon right here, so I can scroll through and I can look for glucose in here. And I can look for glucose in there. I've got C3H6 here, I got C3H8 here, but I need a C6 up here. Here's C6H6, but I need C6H12O6. Oh. Did I miss it? No, I didn't miss it. It doesn't look like it's up here at all. Well, this is why Google exists. DuckDuckGo works, but Google works a little bit better even. Search for the standard enthalpy of formation of glucose. The miracle of Google is it doesn't just give you the answer, it gives you the answer right up front. Negative 1273.3. Standard enthalpy of formation of glucose is negative 1273.3 kilojoules per mole of glucose. This tabulation of standard enthalpies is a very powerful thing. We can use it not merely to predict these highly theoretical reactions. Most of you know that we don't typically generate glucose by combining pure carbon and pure hydrogen and pure oxygen. Glucose, more often than not, comes from the reactions in photosynthesis and comes from the reaction of carbon dioxide combined together with water to release oxygen and release glucose. So what we need to do is we need to see how we can work out reactions of that sort, work out the energetics of reactions like that sort. And there's a powerful tool that we have called Hess's law. And we'll describe Hess's law and how Hess's law works when we get back together on Tuesday.